Hey, welcome everyone. This is a mechatronics lab tutorial. We're going to talk about stepper motors. I've got a stepper motor system here that we're going to work with, and we're going to look at some of the basic coding to make our stepper motors work. Right off the bat, you can see we have a three-axis stepper system. Right now it's running. We have here our Z-axis, vertical axis, we'll call that the Z. We have this translating left-right axis, we'll call that Y, and then X. So we've got an X, Y, Z, cartesian, gantry, stepper system with these nice, I pointed out a couple times, we've got these nice ball bearing lead screws, stepper motor, direct drive, no gear heads on these, probably Nema 23. Got coupling, flexible coupling here. The slide is built on this 80-20 extruded aluminum with linear rails supporting it. So this is a nice setup mechanically to support large loads. Over here, I've got the drivers. At this end, you can see down in here, I've got my ATMega 2560 that's controlling everything. We're running everything off the ATMega, so you can plug in, and if you wanted, you can plug in and test code on this driver. And then I've got four stepper drivers here. These are the DM556N stepper driver, just kind of a basic stepper driver here. I've got four of them because even though it's three axes on this setup, I've got two steppers that I'm going to run in sync to show the x-axis. Okay. So with no more delay, let's get started with some basic coding. Oh, and you can see it's running something there. We're running a motion profiling. Running in motion profiling on just the z-axis. And if you can see, I'm achieving some linear speed, but at the ends, I'm going to blend that speed to rest, blend it back up. These are parabolic blends. Parabola means second order equation, or first order linear in velocity, constant acceleration. That's the go-to method in motion control. So we'll start with a blank ATMega code here. Show that over on the side so we can keep our eye on it. Okay, and I'm going to start with some comments. So this is going to be our stepper motor driving example, and it's built on the XYZ gantry. Steppers driving lead screws. In this case, we're using the DM556N stepper driver. And that driver has three parts. It's got a direction. It's got a step line. It's got a direction. It's expecting direction and steps. I'll say a direction line, if you will, and a step line. And on the step line from the spec sheet, I'll say this. And right now we're configured for half stepping. Half stepping for 400 steps per rev. And we did that with, there's dips, which is on the side that we chose. On this stepper, from the spec sheet, the stepper says that that steps occur are triggered by a falling edge on the step line, and it needs a 5 microsecond, if you will, a stabilizing at high before falling to low. So it needs a falling edge, but it's going to catch. It needs at least five microseconds at a high state before we'll trigger in that dropping low. Our hardware is configured as follows. Also is connected as follows. We have our z-axis is on the PB7 is our direction, and PB6 is our step. The y-axis, we have PB5 is the direction, and PB4 is the step. And then finally, the x-axis, PH6 is the direction, and PH5 is the step. And this goes to two stepper drivers for the x-axis. We mentioned it. Okay, now I'm ready to get started. I'm going to create first some global variables. And I'm going to create a DT, a variable DT. That's going to be our time step, a count, I'll call CNT, and then a number of steps, which I may use. And this is my time step, respectively, time step. If you will, the time step or step time between steps. And then count will just be a counter. And then num steps would be just the number of steps to count. I guess it's kind of obvious from the name. I'm going to have a direction line. I'm going to make that a Boolean. My direction. It's either 1 or 0, meaning if you will forward or reverse. All right, next, using the since we're using the Arduino software, we don't have a main. We've got a setup and setup in a loop, kind of odd, but here we have it. So in my setup, I'm going to I need to make my DDRB equal to outputs. And since I'm only using PB7 through PB4 as outputs, that's what I'm doing here. So PB4 to 7 are outputs. And I need the same thing for H. So so PH5 to 6 are outputs. By not setting everything else, there's a tad bit of power savings there, perhaps. So I'm only turning on the ones that I need at this point. For B, I'll initialize to 0. And I'll do the same for port H. And then I'll initialize my counts. Direction, I'm setting to 1. Some more initialization. My DT, I'm going to start at 500. I'm going to use the micro delay. I'm going to use that. I am going to use that Arduino function. I'll try to avoid them, but I will use that one. So this is going to be my speed, and the speed is going to be defined as the speed will be given as step per DT in the units of microseconds. And since we're 400 steps, and if we want to get that in revolutions, we could say step per DT in microseconds times 400. Well, I guess I'd have to divide, wouldn't I? Times 1 revolution per 400 steps. That would give me revolutions per microsecond. You want to think about it. I don't know that that's a terribly useful number, but that's the basic idea. And then I've got to choose how many steps. So let's just say number of steps. I'll just start off with 1,000. 1,000 steps. If we're in half stepping mode, 400 steps, that should be 2.5 revolutions is what that should give me of my motor or my stepper. Okay. And call that good. Now we're going to put our main code here. And in our main code, what we want to do is drive our steppers. Steppers. So let's first drive. We're going to drive or move the z-axis. We'll start with the z-axis and then we can add more. And in this case, I'm going to just make we're starting with the more simple case possible. I'm going to drive one axis at a time. Right now only the z-axis moving. I'm going to start there. Later on in these tutorials, I'll show you how we'll do coordinated motion, and I'll show you how we'll do profiling motion. But at the moment, we're starting straightforward. So since I'm just moving the z-axis, I'm going to run a loop. So for count equals 0, count is as long as count's less than the number of steps. Just tighten up a little bit here. And count plus, so I'm indexing count. And now I'm ready to start driving it upward. The first thing I need to do is choose the direction. So I'm using port the z-axis. So the direction on the z-axis is PB7. So I'm going to let port B equal, and I'm going to use a logical shift left. I'm going to take my direction and logically shift it to the PB7 location. So I'm setting the direction z-axis. Next, I'm ready to send my, so there I just set the direction. Now I'm going to send pulses to the step line. First thing I'm going to do is bring the send the pulse line low. So I'm going to say port B. And I need to drive it low. So I'm going to set this pin only low. I'm going to do I'm going to AND port B with a mask 0B for the step line on PB7, or excuse me, the step line on axis 7 is PB6. So I'm going to mask this with a 0 in the 6th bit. 2 minutes here. Okay. And this will set PB6 low. PB6 low. Then per the spec sheet, I'm going to hold this low for 5 microseconds. Now I know above I was saying stabilized by holding it high. I believe actually stabilized by holding it low. We'll have to go back and look at that to confirm, but I'm going to stabilize it by holding it low for 5 seconds. Per spec sheet to the with 5 microsecond delay. And then I'm going to bring the port back high. And I'll do that with an OR equal. My same mask, 0B, 01, 00. So now I'm set PB6 high. Set 6, type 7, I'm at 6. Okay. And then I am now done with this step. This isn't MATLAB. So in that loop. And then at this point, I believe I'm happy with that. So I'm driving it in the, I start in the 1 forward direction. So I'm going to drive it 1,000 steps upward. I do that by setting the direction to a 1, which is, we'll say forward. I'll set the bit low, hold it for 5 milliseconds, set it high. Oh, I need to do one more delay according to my speed. So I've got to do a delay, microseconds, DT. Okay, so this is a delay of DT to set the speed. And then I'm done. So I just keep doing that until I've completed the, in this case, 1,000 steps. Now, when I get done with that, I would like to change the direction and then repeat. So to do that, by default, my loop has the repeat built in, but I need to change the direction by setting direction equal to the not of direction or the negative. I suppose either one would work. So here I'm changing direction and I repeat. Okay, so let's go ahead and try this. I'm going to connect to my port. Looks like I'm connected. And I will, okay, this is stepper demo 3. Call it part 1. Maybe that means we're going to do a couple parts here. And of course, I have some errors. Guess it wants a comment up here. I have another error. Get too many of these things. So there's braces. It's compiling and it's going to send it directly to our driver. When it does, should take over and we should get some new motion according to what we just created. Okay. This is the program we have just built. Okay. Now, there's a couple observations that we'll make. First of all, it's running maybe a little fast, a little clunky, so I'm going to slow it down. To slow it down, I'm going to increase this delay. I'm going to go ahead and make that 1,000 microseconds. Let's see if we can see the difference. That should cut the speed in half. Watch it carefully, see if you feel like that's the case. Looks fairly reasonable. Here it looks as if I've cut the speed in half. The second thing is, I said that we were doing 1,000 steps at 400 steps per count. That should be 2.5. That should be 2.5 rotations. I'm going to come over here and see if I can count them. Yes. The very approximate guess, that looks like I've got 2.5 rotations. Let's see if I can, I'm going to even slow it down a little more. Let's cut the speed in half again and see what we get. Each time to change it, I'm, what am I doing? Yes, and now I can see by just looking, I'm getting that 2.5 rotations, and you can see my speed. Now let's go ahead and see if I can make it go farther. I'm going to actually double the distance it's traveling. Right now it's traveling 2,000 steps or 2.5 rotations. I'll now make double that, make that 5 rotations, keep that same slow speed. We'll observe the behavior here. Now it is moving in stepwise motion. It doesn't really know its position, it's always a relative position. So far, I've gotten lucky. I've started it in a condition where it, doesn't hit anything, but you can see the basic idea. So I can see my steps working. I can see the motion. I can see the speed working. Now I'd like to explore speed a little more. We'll keep this larger number of steps. Let's start slowing the speed back down. We were, I'm going to go back to 1,000, which was 1 step for every, really 1 step for every millisecond. That looks clean. Okay. If you hear, I hear a little clunk at the very end. The clunk is occurs here. When I get to the end of my count, I'm going, say, up or down at full speed. I change the direction, immediately start going in the other direction. I have an instantaneous change in speed. That means an infinite acceleration. It seems okay. If I continue to increase my speed by decreasing this delay, we can observe more what happens. Or just cut it in half. That clunking was it reaching the end of travel and not being able to go any farther than the step removing. Now at the ends, I can hear a much harder clunk. And actually even looks like the thing is shifting just a little. And it's shifting because I'm actually losing steps. I'm not able to accelerate fast enough to keep up with this loop, at least for the early part. To accentuate that more, I'm going to cut the speed in half again and see what happens. I'm saying to myself, how fast can we go? Okay. It is not happy with that speed. Let's see if we can back up a little bit. Let's go to a 400 or steps per 400. Um, See that once it comes up to speed, it's okay, but it's having a hard time getting going. If it can get going, it seems okay. But so really the problem is not the travel speed in the middle, it's the travel speed in the middle, it's the ends, it's the acceleration that I'm pulling from. I just can't meet it. Frankly, I would call this a bang bang control, and frankly, even this 500 step per 500 counts, that's not even very accurate. I'm not quite there even. So with this very basic control, it's still marginal in terms of working reasonably well. Let's find something that with the bang bang control at least would seem like it would work. Okay, that doesn't seem too bad. So step or half step, we'll call them a step. We're making half steps. One step per 750 microseconds seems like a speed that this thing is able to accommodate, at least with no load on the end. Okay. Well, let's go to the next step. Actually, let's stop this video. We'll call this our very first segment. So hopefully there was some interesting tidbits you picked up here, and thanks for joining.